Hello, this is David Harper of the Bionic Turtle with a quick introduction to linear regression. There are three basic steps in a linear regression. First, we look at the scatter plot. Second, we perform the regression analysis, which generates estimates of population parameters. Third, we interpret that analysis. Why do we start by looking at the scatter plot? First, because there may be a relationship between our variables, but the relationship may be nonlinear. Here's an example of a nonlinear relationship. If we would look at the scatter plot, we would see that it would save us the time of going straight to a linear regression, and we could instead use other nonlinear techniques. Second, a quick look at the scatter plot may just tell us there really is no relationship, as in this data that I randomly generated. Doesn't look like a relationship, so I'm not going to try a linear regression. Now, on the other hand, here's actual data that I pulled. On the y-axis, hedge fund returns from the HFRI hedge fund index, regressed against, or in this case, just plotted against, returns from the Russell 3000, a good proxy for the overall market. And a quick look at the scatter plot, at least to me, says this looks like a linear relationship and therefore worthy of a linear regression. And so the linear regression, in this case, draws a line through the data, and that line represents the best fit. There's a purple line here because this plays a role as well, and this is just the average of the y values. But the red line is the regression, and it is expressed by the linear regression formula here, given by y equals alpha plus beta multiplied by x plus epsilon in this case, which is the error term. So the error term plays an important role. So that's the linear regression. It's a best fit line. How did that line get generated? Well, typically by ordinary least squared methods. And so if we take one of these observations, like this observation right here, and look at the distance from that observation to the regression line, if we take that distance and square it, and then do the same for this next observation and for each of these observations, and so we can call that the distance the error between the actual observation and the y as predicted by the linear regression, we can square those and sum those. That gets us a big number. This line attempts to minimize that number. Ordinary least squared attempts to minimize the sum of the squared differences between the actual observation and the predicted y on the line. So this is the linear regression formula. Pretty simple. I show it here three ways because sometimes we see it with different notation and we don't want to be thrown by the notation. These all mean the same thing. In some cases the intercept may be Roman A or Greek alpha or even B sub 0. But in all cases, if I just take this first one here, we have y, the dependent variable, is a function of or equal to the intercept. That's the y-intercept. Where does that line hit the y-intercept? Plus the slope, that's b or sometimes beta, multiplied by x, the independent variable. So we can say y is dependent, x is independent, y is a function of x, or the way I like to think about it, y depends on x. And finally, don't forget the error term. The error term reminds us that this line, it will never be a perfect fit. There is error or dispersion between the actual observations and the line. Realistic data will never fit on the line tightly. So error captures that dispersion and reminds us that this is just a prediction of y. This formula, intercept plus slope multiplied by x, is just a prediction of y. The actual y is going to be some error off of that. So, to summarize, x is the independent, y is the dependent, and the error term is the residual that reminds us x tries to explain why, but cannot fully explain why. So that's a quick introduction to the linear regression equation. This is David Harper of the Bionic Turtle. Thanks very much.